it going? Oh, really? You just need to the first one.
No, I hadn't seen it. It was from like
The 17. Wait, but this is oh, that's easy. Even then.
So if you do like a picture,
It's really see 2 and 3 is like
it's like the same.
F3 I.
True, I know. Oh, that's what easier. I that's okay. That's like 160 something. Unless the other way to do it is 2 years later, I saw that on I was like, I have terrible news for everyone. It's been fun there. Just kind of
Oh, those. Oh, for the this one. Okay, good afternoon. I think we should start. So I have brought the your graded quizzes, and so later after our class, you can come to fetch your own. For someone who will not show up in this class and can get the quiz during office hour, but unfortunately I'm not available in tomorrow's office hour, so the TA will schedule the office hour like between 10 a.m. to 11 p.m. 11 a.m. in the TA room. So you can go to the TA's room and ask for any questions regarding the homeworks and other problems. And that's the first thing. Second thing is just a reminder again. So on next Wednesday, we'll have a second quiz, which could cover all we have discussed so far after the first quiz, but it won't directly cover something we discussed before the first quiz. So if you like, you can start to prepare your cheat sheet. So again, it is a single-sided cheat sheet. You can write down whatever you think that might be beneficial to the quiz. You're not allowed to use laptops, calculators, and cell phones, and etc. So I will make an announcement again during this weekend or next Monday to ensure every one of you will show up. Don't miss your quiz. That's a loss for your final grade. Okay. So let us talk about the class content. So in the last lecture, we have finished reviewing linear algebra. There were very basic mathematical operations on vectors and matrices, and you should be familiar with linear algebra because it is extremely important or fundamental in data science and machine learning. If you take some, if you will or you plan to take some machine learning class, or you want to do some work regarding building up machine learning models, you will find that nearly every model, every specific model, every loss function is expressed in terms of matrices and vectors. Usually it won't be expressed as like single scalars. And also the computation, like optimization or derivation are all expressed in terms of matrices and vectors. So that means that you should be familiar with like matrix derivatives. Okay, so today we will start with a new topic. It's called linear regression. So this is I think perhaps the most fundamental topic in like all branches of data science or statistics. So if you have taken some statistics course before, you might have already learned the linear regression models. So what is regression? So let us first clarify the concept of regression. So what does regression mean? So it simply means that I want to do prediction, and the interesting variable we want to predict is continuous. then this is called regression. Very simple. I want to use a large set of variables to predict another continuous variables. This is called regression. For example, I want to predict tomorrow's temperature. The temperature is continuous. It's real value, so it is a regression. I want to predict Apple's stock price, like after new Apple is released, then this is a regression because stock price is continuous. Like I want to predict the annual income of the families in Salt Lake City. This is regression. So regression is just a special type of prediction. So obviously, in practice, we're also interested in predicting like discrete variables or binary variables. I want to predict whether the economic growth will be positive or negative. And I want to predict whether I will earn money next year. This is a binary variable. So this kind of prediction is called classification. So you will see that there's essentially not that difference between regression and classification. Just they are all prediction tasks. And prediction task is actually some core task in like machine learning or data science or artificial intelligence, whatever. And in the future, you will learn all kinds of complex prediction models, like deep neural nets is a kind of prediction model. Then what about linear regression? As the name suggested, linear regression means that I want to use a linear model to perform regression. That is to predict continuous variables. This is called linear regression. So correspondingly, we have a linear classification. And although linear regression or linear classification are very simple from the modern perspective, they're really simple, but they are very widely used. Even nowadays, you heard a bunch of buzzwords like artificial intelligence, like deep learning, those kind of things. But I believe, from my own point of view, this one is much more widely used than all kinds of buzzwords you have heard. Linear regression, linear classification, very widely used. Most time you just don't realize the existence of these models. So to introduce linear regression, we'll start with the simplest case. That is, we'll consider regress a target variable with only one variable. So suppose I have an x. Right? I have a one variable x. I just want to use this single variable, this is scalar, to predict our target variable y. The simplest task. And we call this variable x explanatory variable. And the target variable as a dependent variable. So the name is quite intuitive, right? We assume that x can explain the target variable y, so we call it explanatory variable, and the y depends on x, so it's called dependent variable. So now, we want to use x to regress y, and we want to use linear model to do that. Then can you work out such a linear model? Can you work out some general form of the function of x to express y? An idea?
A is supposed to be
Hey, what?
ax plus b.
Yeah. Yeah, perfect. So this is exactly linear regression model for this two variable case. So linear model means that, okay, I want to express y as a linear function of x, right? Then what is the most general form of this linear function for this single variable? Ax plus b. It's pretty intuitive. We have a coefficient for x plus a constant b. And we assume the relationship between our dependent variable y and the explanatory variable x expressed by this linear function. So what does this linear function represent? Geometrically. Yeah, a line. It's from what we have learned from high school. This actually represents a line. And what does A and B? What do A and B mean?
Slope and intercept.
Yeah, slope and intercept. This B and the slope. We know that the slope is a tangent of the angle, right? Is A. So this is a graphical representation for our linear regression model. So what's the general procedure to apply the linear regression? So we usually perform 3 steps. So first, we collect a set of training instances. So what are the training instances? Namely, the observed pair of x and y values, x1, y1, and x2, y2. Suppose we have collected like n training instances, meaning that we have collected n pairs of explanatory and dependent variable values. So let me write it more clear. Does it look clear to everyone? Okay, this is the first step. This is called training data collection. Actually, these 3 steps apply to any kind of regression models or classification models. And what is the second step? The second step, we want to identify the most appropriate linear regression model out of this training. This procedure is called fitting or training or model estimation, whatever. They have a lot of words, but they basically name the same thing. So fit the linear regression model to the training set. So basically, the target for the second step is to identify the most appropriate slope and intercept for our linear regression model. How can we do that? Suppose we have a set of training instances. It's x1, y1, x2, y2 to xn. And they actually represent n points in this 2-dimensional space, right? So let me just random draw those points. So suppose we have those set of training instances. So roughly speaking, the fitting procedure is to draw a line. Okay? Draw a line to be as close to those training points as possible. And then we pick up the corresponding slope and intercept to get specified linear regression model. So this is the second step. This is usually called training. And third step, prediction. So now that we have our specified linear regression model, then for any new values of x, say x star, right, we can use our linear regression model to predict the corresponding value of the dependent variable, right, y star, right? How can we predict? We use this linear function, right? So our prediction will be ax star plus b. So these are the three steps for using the linear regression model. So, but basically, you can apply the three steps to any regression model like neural nets. And neural nets, you won't have such a simple linear form. Right? That could be a very, very complex nonlinear form. But the application of neural nets also follows three steps. We collect a bunch of instances, training instances. Then we fit a neural net model to those training set. And then we can do prediction. So now, we'll first take a look at a detailed example. And then we'll show how we derive the optimal slope and intercept that fit the training set. And then we'll implement this fitting procedure with Python and show you the result. So this specific example is to predict a person's weight according to his height. So when so in this case, the explanatory variable will be the height. So let me denote it by h. And then we want to predict the dependent variable will be the weight. When I was a child, I read from a book or magazine, I cannot remember, that there is an empirical formula saying that given your height and your normal weight, meaning that if you are healthy, your normal weight would be your height minus 102. So here, height is measured in millimeters. It's 102 millimeters. And the weight is measured by kilograms. So because I was born in a place that use a metric system, it's not here, like using pounds and inches or feet. So I was quite impressed by this formula. That's why I still remember it right now. And every year I try to apply this formula to calculate my normal weight a few times. But when I grew up, I became more and more disappointed because it looks like I'm always overweighting. And so I became a kind of skeptic about this effectiveness of this formula. So this is actually a linear regression model, right? It's a linear function. So now let us look at a set of data points we collected for this weight and prediction. Does it look good? Sounds looks clear to everybody? I can enlarge it. I can enlarge it. So suppose we have finished the first step, namely that we have collected a set of training instances. So here, the heights are measured in inches, and the weights are measured by pounds. It's different from the relationship I just expressed. And the second step, and we can show those training instances in a two-dimensional space, which are represented by those blue dots. Right? And our next step would be fitting our linear regression model to those training instances. That means we want to draw a line, a right line here, right, to be as close to those training points as possible. And after we identify this linear regression model, specifically this line, right, and we can predict the height for a new, the weight for a person with a new height, right, like 69 inches. What is the weight for that person? So this is our task. And so actually, I'm curious if you convert the heights from inches to kilograms, and from inches from inches to millimeters, with from pounds to kilograms, whether it is consistent with the formula I just wrote here. So you can check whether this is correct. But my memory won't be wrong. That's the exact formula I read. Okay, so this is a problem setting. So is everybody clear about this? Okay, so I don't need to turn off right now. So just to keep this task in mind, because we will return to this problem later. So now let us look at this model again. So suppose we have finished step 2. We have identified some specific linear regression model, and we want to do prediction. And then how can we measure the performance of our linear regression model? How can we measure the performance? An idea?
Test it out with new data, we know what the answer should be.
Yeah, and how can you quantify whether your answer is correct or not?
Maybe keep track of the incorrect or the actual answer compared to the expected answer.
The what?
Like, you'll get an answer out,
Mm-hmm.
and then you can compare that to what the actual answer should be.
Yes. How do you compare?
Maybe take the difference between the two.
Yeah, exactly, right? So how can we measure the performance? So suppose I can collect a set of test data points, right? That I know the value for the explanatory variables and also the ground truth value of the dependent variable. And then to measure the performance, I can just do the prediction and then calculate the difference between the ground truth value and our prediction. Right? So let me just copy the prediction here. So it will be ax star plus b. Then calculate the difference. And usually we take absolute value because we don't care whether our prediction is bigger than or smaller than the ground truth value. We only care whether it is close to the ground truth. So this is a way to measure the performance. Obviously, this difference is smaller. Our linear regression model is better. Right? And to get a robust measurement, I can collect many such test instances, right? And then we calculate the error for each prediction and just enrich. So this error is called a residue. It's called residue. And we usually use residue to check or evaluate the performance of our linear regression model. So now, we address the evaluation problem for the third step, right? And then let us go back to the second step. How can we fit the linear regression model to a set of training instances? Namely, how can we find a line that to be as close to those training points as possible? We just say that we want to draw a line, but how can you do it precisely? An idea?
Minimize the residual.
Yeah. You can use the arrow we just defined to guide the identification of this model, namely to search for those optimal line. So here I give the most commonly used objective function to fit the linear regression model. It is called a sum of square errors, briefly SSE. So the SSE over a set of n training instances is defined as the summation of the square residues over the prediction on each training instance. So the first term would be y1 minus our prediction, right? ax1 plus b, and you take square. This is the square error for the first training instance, or square residue. And then plus the square residue for the second instance, which is y2 minus ax2 plus b squared. And we can continue until we add to the last squared error, which is yn minus axn plus b squared. And to fit a linear regression model, we can minimize SSE with respect to A and B, namely the slope and intercept. So we convert it into a minimization problem, an optimization problem. And find the optimal A and B, we end up with the best, the smallest SSE error, and we find out the best line that closest to those n training points in the two-dimensional space. Although I have erased the line. So this is the most commonly used objective function for fitting a linear regression model or even non-linear regression model. But someone might ask, why should I use this square summation, or summation of square form? Can we directly add up all the residues? So alternatively, we can come out a new one, right? A new objective function. For example, I directly ask the residue for each training instance. This is absolute value plus the second residue plus until the last residue. Question: can we use this one? Can we use this objective to fit our linear regression model? Yes. Any other suggestions? answer is yes. Definitely yes. You can do that. And you can even like generalize like to like take every residue to P, right? To a positive number P. You can do that as well. Then the question is why the most common used objective would be SSE rather than all those variables. I can tell you, this is not only applicable to linear regression. Like basically, the nearly all the neural net deep learning training objective have the same form. It's called square laws. The most common used the objective function to train all kinds of machine learning models. Why this one is so popular?
It's because if it's squared, the difference, if it's large, it becomes larger, and if the difference is that large, it's not that big of an effect on the sum.
Well, you present an interesting point, but actually this is something being criticized for the SSE. So basically, you take square. Square of the error means that if there is some outlier, you have some large. If you have some large error, it is enlarged. It is amplified, right? So sometimes it's not very good. Meaning that if you have some wrong instance, it's pretty common in practice. Meaning that some of your training instance is just wrong. It's just some outlier, but that outlier will severely affect your training result. But in many cases, we don't want our trained linear regression or neural network to be so sensitive to outliers. So this is something being criticized for SSE objective. But this is not the scope for our class. So here we just want to advocate the benefit of SSE. So why it is so common use? So the first benefit is that it is easy to compute. Why is it easy to compute? We want to minimize SSE to find out the optimal model parameters, A and B here, right? And maybe for neural nets, it could be like neural nets weights and whatever. And to perform this minimization, what do we need? An idea? If we want to minimize an objective function, what should we do? Yeah, the first step, always take derivatives. So you can say, for this sum of squares, the derivative is very straightforward, right? So you just put 2 here and then take derivative inside this parenthesis. It's a chain rule. It's pretty easy. But what if I want to minimize this sum of residues? What's the derivative for a sum of absolute values? It's not trivial, right? Because we know that if a function is just an absolute value of function, it does not guarantee to have derivatives everywhere. Right? At least for x equals to 0, there's no derivative here, right? How can we compute the derivative? Right? So usually for the practical applications, you have to optimize your objective function with some modern computational algorithms like LBFTS-B, -B, and conjugate gradient descent. All those packages, not all of them, but most of them will require you to provide the evaluation of the objective function and its gradient at any setting of the parameters, so that they can use this gradient to search for the best parameters. If your objective function is not differentiable, then how can you provide a gradient? So the first advantage is that it is easy to compute, easy for optimization. And second benefit is that in many cases, especially our regression model is simple, like linear. We even don't need to fit this objective function into an optimization package. We can directly derive the optimal value for A and B analytically. Actually, we will show it today. And later, when we extend our simple linear regression model to a multi-linear regression model, namely that we have more than one explanatory variables, then we will use vector matrices to represent the linear regression model. And we also have the analytical solution for the optimal regression model parameters. So this is a second benefit. And third benefit actually connects to what we have discussed before. This SSE connects to the Gaussian likelihood. So if you still have some question about what we have discussed in concentration inequalities and central limit theory, so you should still remember that our Gaussian distribution, the sparsity of the Gaussian distribution looks like what? So for a random variable x, which has expectation being mu and variance being v, what's its density function? So its density function looks like this, right? It's proportional to exponential to 1 over 2 and divided by the variance v, right? And then a square, right? X minus mu and then take square, right? So now we can see where does this square term come from. If we take logarithm, meaning that we are doing likelihood, log likelihood. If we take log likelihood, log over this density, and we end up with this square term. And consider that we have multiple random variables which follow the Gaussian distribution. I want to do the maximum likelihood estimation. So doing maximum likelihood estimation, meaning that I want to maximize this square term. Right? Meaning that we want to minimize the square term by removing minus sign here. Right? So maximizing this is equal to minimize this. Right? So now it connects to the SSE form. Right? So if we just expand the log likelihood estimation to like a summation of the log likelihood, we Gaussian log likelihood, when we maximize the summation of a Gaussian likelihood, it corresponds to a form of SSE. So there is a strong connection between them, meaning that we can always give some elegant interpretation about our objective function. It connects to some assumption in the probabilistic models, namely Bayesian models. We can assume, okay, actually this is a random variable, and ax1 minus plus b, this prediction is the mean, right? And y1 is our observed random variable, follows a Gaussian distribution with mean being here, right? And suppose we just ignore the variance, and then when we do the maximum likelihood estimation, we actually minimize this SSE error. So it has a well connection to the probability model. So those three benefits, there could be more reasons that lead to very broad usage of the such form of objective function in fitting regression models. But although this is a pretty dominant in the training fitting procedure, there is some research in finding alternative objective function like this one. If we can solve these computational difficulties in minimizing this objective function, we also get some benefit, right? So this is kind of cutting edge research. So how do you come out with some new objective function? But here I just want to introduce you the most commonly used one. It's pretty mature objective function used in practical applications. So now let us look at our SSE. We want to minimize the SSE to obtain the best parameters, slope, and intercept. As we just mentioned, one advantage of SSE is that we can even analytically derive the optimal A and B. So then let us try to obtain this. So before the derivation, let me first give the answer and discuss about its geometric meaning, and then we show the steps to derive the optimal values. So the optimal intercept and slope turns out to have the following form. So first we define the average of all the x values, so which is denoted by x bar, which is 1 over n, x1 plus x2 until xn, and correspondingly the average of the values of y's, right? Denoted by y bar. And also we can construct two vectors, n-dimensional vectors, which we denoted by x hat. So each element of x hat is an instance x1, x2, and etc. subtracted by the average. So the first element will be x1 minus the average of all x values, x2 minus the average of all x values, and continue. The last element is xn minus the average of x values. So we can consider it as a centered version because they are subtracted by the average of all x values. Centered version of the explanatory instances. And similarly, we can define a centered version for the dependent variables values. So the first element will be y1 subtracted by y bar, the average of y. The second is y2 subtracted by y bar until the last element is yn minus y bar. Okay, given the definition of those x bar, y bar, x hat, y hat, okay, the optimal slope and optimal intercept, which minimize SSE, have the following form. So this optimal slope would be the inner product between x hat and y hat, the centered version of the explanatory and dependent variable values, divided by the square norm of x hat. And the optimal intercept is actually the average of all the y values subtracted by the optimal slope multiplied with average of all x values. So this is a solution by minimizing the SSE. So before we show how we obtain these two formulas, we can first take a look at what does these two formulas mean. So we can first check the setting of the optimal intercept. So let me redraw the file. So suppose this is our training set, those circles. And we have identified the optimal linear regression model with slope A star and B star. So it's here. So first, from the setting of the optimal intercept, what can we conclude? We can do a simple manipulation of this formula, right? So from this, we know that the average of all y values, y bar equals to A star x bar plus B star. Right? Because we can move this term from right hand side to the left hand side, we end up with this. And now what can we conclude? What is our optimal linear regression model? It is a line, right? Determined by the slope A star and the intercept B star. So for any point on this line, it will satisfy this equation. So now we say x bar and y bar satisfy this equation. Then what does it mean? It means this point stays on the line. And what does this point mean? So x bar is the average of all the x values, x1, x2 to xn. Right? So if we want to identify this point, we just calculate their x coordinates and the average. Right? So we got the average of x here, right? And also, similarly, we can obtain the average of y values by looking at the y coordinates for all the points, right? So it could be here. And then this is our point, x bar, y bar. So x bar, y bar is actually the center of your training data set. Center of your training data set. You just average x values and y values, you get center of the training data. So the first conclusion, which is interesting, is that in this optimal linear regression model, the center of our training instances or training points stay right on the line. And second, what can we say about the meaning of the slope? What does this slope mean? What does it? What kind of interesting stuff is reflected by the setting of a slope? So we can consider x hat, y hat. There are two n-dimensional vectors, right? Centered vectors. So imagine an n-dimensional space. Right? So this is a x hat, and this is a y hat. And we can naturally assume there is an angle between them. Then according to the formula we repeatedly mentioned in previous lectures, the cosine of the angle is the inner product between the two vectors divided by what? Norm of x hat multiplying with norm of the y hat. So now, let us try to move the norm of y hat to the left-hand side. So we get norm of y hat multiplying with cosine theta is inner product over norm of x hat. Now we divide both sides. We divide both sides by this norm again. So we end up with this, right? So let me make this equation. Let me just copy it down to make it look better. Right? So it's inner product between x hat and y hat and over norm of x hat squared. So what is the y-hand side? It is the optimal slope, right? It is the optimal slope. And then let us look at what does the left-hand side mean. So first, what does the numerator mean? Take a look at the graph here, right? So remember, the norm of y hat represents its length. So if you multiply length of y hat with cosine theta, we actually ends up with the projection length. The projection, if you project y hat to the direction indicated by x hat, and the projection length would be a norm of y multiplying cosine theta. And then you divide this projection length by what? By the length of x hat itself. So let us color it with blue. So this is the length of x hat. Remember, norm represents length, right? And then it is clear about the meaning of the optimal slope. So optimal slope is actually the ratio between the projected length and the length of x hat itself. It's kind of ratio. So this is the meaning of our optimal slope A star. Any questions so far? Okay, so then the remaining task is to derive these optimal values. Actually, the derivation is not listed in the course material. That's why I want to guide you how to obtain this result. It's not extremely trivial. So to minimize this SSE, what should we do first? Take derivative, right? Take derivative as we previously mentioned. So we should take derivative over both A and B. Right? And then solve the derivative being 0, we end up with our optimal A and B. So what's the derivative of SSE with respect to A? We can take derivative over each square term and add them together. It's pretty straightforward. So what's the derivative for the first term? To multiply this difference, right? So it's 2 multiplied y1 minus ax1 plus b, right? And then apply the chain rule because the coefficient multiplying with x1 is multiplying with a is minus x1. So we should multiply this term with minus x1. And this is the first term, the gradient for the first term. And then we take derivative for the second term. Following the same procedure would be 2 times y2 minus ax2 plus b and minus x2. And we can continue. And it's pretty mechanical. Thus, until the last derivative, which is 2 for the yn, right? Minus axn plus b times minus xn. So this is a derivative of SSE with respect to A. And similarly, we can derive the derivative of B. So again, we take derivative over each square term and apply the chain rule. But for B, we know the coefficient for b is just -1. So here we won't multiply minus x1, minus x2, and etc. We just multiply with -1. This is again, it's pretty mechanical. So it's 2y1 minus ax1 plus b, and chain rule here, and the coefficient for b is -1. It's -1. And second term, we just follow the same format. y2 minus x2 plus b -1, and continue until the last term, which is -1. And we know that when we have the value a star and b star, those two gradients or two derivatives are exactly 0, right? So we can first take a look at this second derivative. So when second derivative a and b take a star and b star, it is 0. So let's just put star over them, and we know they are 0. Right? Now let us try to derive the relationship between a star and b star. So first, we can remove 2 and -1 on both terms, because on every term, because they are multiplied with every term. So we can remove it. And now let us try to add up all the values for y. So we have y1 plus y2 plus plus yn. And then we add up all the parentheses together, namely the prediction of our linear regression model. What do we have? So first, we'll multiply a star with the summation of all x values. So it is x1 plus xn. And second, for each term, we are subtracted by b star, right? And we have n terms in total, so we're subtracted by b star for n times. So finally, we ends up n multiplied by b star. And we know this is 0. And then we divide both sides by n. So it becomes n, and n over n is 1. And then what can we get for b star? We just move b star to the right hand side. So we get b star. So now what is this? Yeah, this is y bar, right? This is the average of all the y values. And what is this? X bar, average of all the x. So we now end up with the first formula, which I have already erased. So let me copy the answer here for you to compare with. So we know the optimal slope is x hat, y hat, inner product over x hat norm squared, and the optimal intercept is y bar minus b star multiplied with x bar. So from this, we have already derived the second formula, right? Minus a star x bar. So this is pretty straightforward. So now, let us try to get the first one. The first one is not that obvious. So to get the first formula, to derive the first formula, we should look at the derivative with respect to A. Meaning that when we take A, B to be A star and B star, this derivative is 0, right? So now the first thing we can do is that we can remove the constant factor -2, right? Because they are multiplied with each of those terms, right? So for convenience, let's just remove them. So inside this parenthesis, there is no minus sign anymore. And second, we can utilize the formula we have just derived here, the relationship between the B star and A star. So to be clear, so now we can replace B star by this, right? Y bar minus A star X bar. And what can we get? So let us look at the first term. So now B star is replaced by the right hand side, y bar minus A star X bar. So just replace y1 minus A star X1 plus B star is replaced by this. So it's y bar minus A star X bar. And then we should multiply with X1. So this is the first term. And we can follow the same form to obtain the second term. So y2 minus A bar A star X2 plus y bar minus X times X2. And continue until the last term. Xn plus y bar minus A star X bar times Xn. We know this is 0. So actually, we can see this is actually a weighted summation. So the left term is weighted by the value of the explanatory variables x1, x2 to xn, and their weighted summation is 0. And we need to observe right now is that what we need to observe right now is that if we take off those weights x1 to xn, and the what will be the summation of all the left terms? Can anyone observe? If we add up all the left terms, namely this term, until this term, without those x1, x2, xn, what will be the result? We can take a look, right? We can take a look. So first, we can add up y1 to yn together, right? So if we add left terms together, so first add up all the y values, so we get y1 plus y2 plus yn. And now let us add up the second term. So they share A star, right? So we have minus A star, and the summation of all x values. And third term. If we remove parentheses, actually we should remove minus sign in front of y bar, right? Meaning that for each term we subtract y bar for one time, and for n terms we're subtracted by y bar for n times. So when we add them together, we have n y bar. And finally, the last term, what can we get? They still share A star, right? And for each term, so here minus minus become positive. We add x bar each time. So add it for n times, so ends up with n x bar. So this is summation. And then we can look at what's the result of this summation. So first, contrast these two values. Right? What's the summation of y1 to yn subtracted by n times y bar? Yeah, it is 0 because y bar is an average. Right? You multiply average by n is the summation of all the values. And then what is these two terms? If you merge them together, you actually subtract n x bar by the summation of all x values. It is 0 again, right? So actually, this term is 0. So what's the meaning for this? What's the meaning for this observation? Meaning that if we remember this weighted summation. Weighted summation won't be 0. We just add all the left terms together without any reduction terms, x1, xn, we end up with 0, right? This is 0. But now, if for each term, each left term, we multiply with a constant, it's still 0. Right? For example, I multiply a constant, that is a negative constant, minus x bar. Right? And here, it's still 0. Why? Because we can take out x bar outside, right? And then merge the left terms together, it is a summation. And this summation is 0, so it is still 0. Any question at this point? Okay. But the key point is that we should observe that the summation of this last term is simply 0, so that we can just put a constant factor here. Because this factor is shared by all left terms, so it means that the computation is simply as another 0 constant. And now, let us try to manipulate this term. Right? So first, left-hand side term. The left terms, we can arrange it as the first term as y1 minus y bar. Right? Minus a star x1 minus x bar. Then times x1 minus x bar. This is the first term. It's just merge the terms. You put y1, y bar together and x1, x bar together and take out a star. And the right term is just x1 minus x bar. Then you plus the second term, follow exactly the form. Minus a star, x2 minus x bar, x2 minus x bar. We continue, and the last term will be yn minus y bar minus a star, xn minus x bar, xn minus x. This is 0. So now, can you connect it to some vector computation? So we can multiply each term with the first parenthesis. So what can we get? So for the first term, we will multiply x1 minus x bar to each of the two terms. We have y1 minus y bar times x1 minus x bar minus a star x1 minus x bar. and square, right? Because this one times this one is square. So the second term is what? y2 x2 minus x bar minus a star x2 minus x bar squared. And we can continue until the last term. And solving this equation, we'll end up with this is a trivial. So the numerator would be y1 plus y bar x1 x bar summation together until yn y bar times xn x bar, and divided by what? x1 minus x bar squared plus x2 minus x bar squared plus xn minus x bar squared. So what's the numerator? What does the numerator mean? It's the inner product, right? So the numerator actually is y hat and x hat. Remember, y hat and x hat is defined as a centered version of those explanatory variables and dependent variables. And what does the denominator mean? Sum of squares is the norm squared, right? So norm squared of s hat. This is how we arrive at this optimal slope. So you can try to follow the this derivation and try to practice to derive it. And it's not trivial until you realize the summation of the left term, as we just mentioned. I have erased it, is 0. Otherwise, it's not easy to arrive at this step. Okay, so in the last let us spend like 3 minutes to introduce how we implement this simple linear regression model in Python. Okay, remember the problem we just mentioned, right? Using the height to predict weight. Right? We have collected here like 10 training instances. That is the height and weight pairs. And now we try to implement our simple linear regression model from what we have just derived. How can we implement? So let me explain this code line by line. So first line, we need to do the matrix of linear algebra computation. So we import the NumPy library, and here x and y are the training instances. So here is the x are all the collected instances for the heights in inches. It is actually this column, and y are the corresponding weights in pounds. So it's right here. So now we know that to compute the best linear regression model, we have the formula. Right? We have a formula we just derived. Right? So we need to first calculate the average of the heights and widths. Right? So this is actually x bar and y bar. So you calculate average by calling non-K average function. And then you get the centered version of those widths and heights. So xk, yc here represents the x hat and y hat. We have just derived. Do you need me to write down the formula again? So that it is easy for you to contrast. So the optimal slope is the inner product between the centered version, which is x hat y hat divided by the square norm of x hat. E star is actually average of all y values minus a star times the average of all x values. This is what we have just derived. So when we translate it into our code, it corresponds to this line, right? So average ABE underscore x is average, that is x bar. Similarly, y bar, and this x hat and y hat. So x minus the average of x, y minus the average of y. And then to compute the optimal slope a star, it is numerator is the inner product, right? So it's dot. You call the non-bit dot function xc yc, and then divided by the square norm of x hat. X hat is xc here. So square norm can be computed by inner product of the vector itself, right? So we can simply compute the dot xc. And then given the optimal slope a here, we can compute the optimal intercept, which is the average of the y values subtracted by optimal slope multiplied with the average of x. So now we finished implementing our first machine learning model, although it's extremely tricky. So we can take a look at what's the value. So the slope is 8.87, and the intercept is minus 427. It's pretty large. And now using this model, we can do prediction. Remember our task is that I want to predict the weight for a person who has 69 inches. So to do the prediction, we just use the linear regression model, right? So the prediction would be 8 times the past height, which is 69 here, and plus the intercept we have just learned. So let us look at what is our prediction. It's 184.9, 185 pounds. It's not small. Okay, we'll stop here. And